Alright, just to show that I am fair, I have poked fun at Jackson, Griffiths, Goldstein by running their textbooks through Google Translate several times to see what comes out. Just to show that I am fair, I am going to do the same thing with sections from my PhD dissertation. This is Conductances in the Two-Impurity Anderson Model by William Bryan Lay, May 2008. Chair James Kevin Ingerson, Major Physics. Let's start, shall we, with the abstract. I have not read this document, really, since submitting it. I think I've pulled it out and paged through it in class a couple times. Every time I read it, I find typos. Well, it's going to get even worse now when we start putting it through Google Translate. Okay, this is going to take a little bit of editing to get rid of these line breaks. So I'll probably put this part in fast motion. Okay. In a number of systems of interest that involve magnetic atoms and their analogous quantum dot manifestations, there arises a competition between Kondo screening and various types of magnetic ordering, direct and induced. This competition can be studied in detail using scanning, tunneling microscopy. Sidebar, you have no idea how many times I said scanning, tunneling microscopy. To probe the clusters of magnetic atoms on metallic surfaces, and has direct implications for systems of double quantum dots. In both of these cases, an observable quantity of interest is the electrical conductance, which can be calculated by applying the numerical renormalization group to the two-impurity Anderson model. Depending on their separation and the strength of their exchange interaction, pairs of magnetic atoms may exhibit ferromagnetic or antiferromagnetic alignment of the impurity local moments, in some cases leading to a two-stage Kondo screening process, effectively isolated impurity screening, or a complete suppression of the Kondo effect. These behaviors have different signatures in their differential conductance. A class of double quantum dot devices composed of a Kondo-like dot and a weakly interacting dot is predicted to display a splitting of the Kondo resonance and a pair of quantum phase transitions. These behaviors introduce unique signatures in the device conductance when the level energy on either dot is varied by tuning the appropriate gate voltage. This work demonstrates that double quantum dots can provide a controlled experimental setting in which to study quantum phase transitions in a strongly correlated system. Okay, that still made sense to me. I've still got some paragraph breaks in there. Let's try to clean that up a little bit. Turn off the word wrap. There we go. Backspace. Differential conductance. Okay, there we go. That should take care of that. Paste. Okay, there we go. All right, so here it goes into Sudanese. Do I want to start with Sudanese? Yeah, let's start with Sudanese. Why not? And then we'll swap Sudanese over here. All right, let's see what it does after one pass. In some systems of interest involving magnetic atoms and the embodiment of analogous quantum dots, competition exists between condenser filters. Ooh, I didn't say anything about filters. And did I? What got translated as filters? I guess that's screening. Yeah, I guess that's kind of like a filter. Anyway, and various types of magnetic, direct, and induced formation. This competition can be studied in detail using a scanning tunneling microscope. Wow, scanning tunneling microscope made it through? Jeez. To probe a group of magnetic atoms on a metal surface and have different implications for a double quantum dot point system. A quantum double point system. It's not a double quantum dot system, it's a quantum double point system. In both cases, the visible quantity of electricity is an electrical act. Ooh, it's an electrical act! Which can be calculated by applying a renormalization group to a two-dimensional Anderson model. No, two-impurity Anderson model. Okay. Depending on their separation and the power of continuous interaction, pairs of magnetic atoms can indicate ferromagnetic or antiferromagnetic alignment of local impurities, in some cases following a two-stage condensation filter process, multiple filtration filters, or complete deviations of Kondo's influence. These behaviors have different signs of differential treatment. The class of double quantum doubles, is made up of Kondo dots, and very weak dots are predicted to show the Kondo resonance split and a couple of phase quantum transitions. This behavior introduces a unique signature on the device conductor when the energy level at either point is varied by setting an appropriate gate voltage. This work suggests that quantum dots can provide experimental control for studying quantum phase transitions in a robust system. Surprisingly, that didn't lose a whole lot. Let's see how badly we can destroy this. Let's see, we just did Sudanese. Okay, let's do Indonesian. There we go. All right, go from Indonesian to Uzbek. Very good. Now Uzbek to Italian. Very good. And we'll go from Italian to Haitian Creole. All right, we'll go from Haitian Creole to Vietnamese. Go from Vietnamese to, let's go Yoruba. Click. Let's see. Let's go into Hindi. Yes. All right, swap that around. Let's get a couple more. Let's go Bosnian. Very good. Flip those around. And finally, Czech. All right. Now the moment I've been waiting for. Czech to English. In some systems, you are interested. Oh, good. Yes. Let's get rid of that passive voice. Yes. In some systems, you are interested in displaying electromagnetic fields and quantum dots. Yes, I am very interested in displaying electromagnetic fields and quantum dots. Competing between capacitor parameters and various types of magnetic flux, direct and inductive. All right. Did I say anything about flux? Magnetic ordering. Somehow magnetic got paired up with flux. With this smoke detector? Where in the world did smoke detector come from? Where did it come from? This competition can be studied to scanning telling microscopy to probe clusters of magnetic atoms or metallic surface of direct systems, double quantum dots. Where did smoke and where did detector come from? I can see how... Oh, I think I know. Microscopy became like scanning instrument. Oh, yeah. Scanning microscope became detector. Clusters probably became like powder or like a distributed set of particles, and that became smoke. Oh my goodness. With this smoke detector... Smoke detector of smoke detectors. Everything is smoke detectors. The competition can be closely monitored to read the magnetic properties of the metal and have a direct impact on the shoe system. All this time I was working on smoke detectors and shoes. I had no idea. Where in the world did shoe come from? High voltage electrical conductance can be calculated by applying... let's see, this is at the end of the second sentence. Direct impact, direct implications for systems of double quantum dots. How did double quantum dots become shoe system? How? In both cases, the electrical potential is the electrical current. Oh, Lord, no. That is not right. That is not right. In both these cases, the observable quantity of interest is the electrical conductance. Okay, so hear me out here. I don't mention current or potential in here. I mention conductance, right? And those are related in Ohm's law, right? So, oh wait, I can't do that on here. Never mind. Right, so V equals IR, so I equals GV. So it's taken G and split it into I and V. Oh my goodness. The electrical potential is the electrical current. So conductance is equal to unity because electrical potential is electrical current, which can be calculated using a band corresponding to the two-dimensional Anderson model. Wow, once it got to two-dimensional on Anderson model, once it turned impurity into dimension, it was stuck there. I wonder how impurity turns into dimension. That's interesting. According to the washing permit. What? Depending on their separation and the strength of their exchange interaction. Where did washing permit come from? So I've got smoke detectors, I've got shoes, and I've got washing something that is so big it requires a permit. The different magnesium atoms may reflect the local properties of magnesium or antioxidants depending on the isolation and intensity of the interaction that's taking place. Where in the world did the magnesium come from? I guess it took metal? Pairs of magnetic atoms, ferromagnetic or antiferromagnetic. Yeah, because I lost ferromagnetic and antiferromagnetic. That got lost. You notice this is also notably shorter, right? Two-step process, filtration or complete staining. Well, yeah, if it's stained, we need to get that washing permit for my shoes. Oh, Lord. Use of a condom. What? I'm guessing it just turned condo into the wrong thing. Maybe condo is condom in one of those languages, and then it got translated to condom. Oh my goodness. Two-step process, filtration, yes, which is what a condom does, or complete staining. Also, sometimes it happens involving condoms. Different behaviors have different properties in this behavior. Oh good, different behaviors have different properties in this behavior. High plasticity. Again, going back to condoms. High plasticity rates are formed by chambers and very weak spots that indicate separation of the chamber to be restarted and converted to several vas. These training devices provide unique conductors with power levels at different locations and gate voltage control. This work shows that quantum dots can provide valuable control for diagnosing digital automation in a comprehensive way. Okay, that got us the beginning. Let's now get the end. Little epilogue here. How long was the last chapter anyway? Oh yeah, I had to write conclusions. So let's grab this text here. We'll copy and paste that in here. We'll grab this one, copy and paste that in here. And you know what? It's actually easier to remove the... Well, no, I should be able to remove these line breaks. Boundaries, tunneling. So this is my last paragraph. I tried to have something that sounded inspirational at the end because the rest of it was so dry. Even after years of progress, the study of magnetic impurity systems continues to yield newer levels of insight and application. With the ongoing development of theoretical methods, such as the numerical renormalization group and parallel computation techniques, and the continuing progression of experimental innovations such as scanning, tunneling microscopy, and quantum dot devices, we will continue to push the boundaries of our understanding of these systems and develop novel applications. Truly, the only limit is our imagination. Alright, let's start with Czech. Let's go Icelandic. And then let's go Swedish. And then let's go Urdu. Very good, very good. Let's go to the beginning of the alphabet. Belarusian. And... Oops, is it not? There we go. All right, now it's back to there. Oh, let's go Japanese. Haven't done Japanese yet. Switch that. Let's grab Espanol. Switch that. Well, let's go Latin. Yes, Latin. Go. And then we'll go to Croatian. And one more. Always got to use Yoruba. Alright. Now this is getting shorter again. Yoruba, back to English. Okay. Despite years of development, discovery, and use of pollution, asthma remains a new understanding. Okay, impurity. I'm guessing impurity turned to, like, dirt, turned to asthma somehow. I do have asthma, so that's appropriate. Through continuous development, both in the scientific terms and therefore in reconstruction, and by numerical simplicity, recently observed in experiments and the result of continuous progress and a microscope, so the Earth exceeds those who read it. and to understand them deeply, systematically. A new application. It really doesn't end there. Fantasy. Well, it does really end there. Thank you so much for watching. I will see you next time. Fantasy.